Howdy, everyone. So today we're going to talk about PETSc. It's a hands-on workshop. So please log in to your HPRC accounts, because what we're going to do, we're going to just do everything together, and then we're going to write your first PETSc code and then the second PETSc code. All right. So before we begin, just a very quick introduction to PETSc. So PETSc stands for portable, scalable, portable,
Extensible toolkit.
extensible toolkit for scientific computing. Okay, so it's a high-level implementation of lots of parallel subroutines that you can use in your computation. It has different parts for different purposes. So for example, DM part, domain management, call it domain management. It's an entity, or it's kind of like a object that helps you generate the grid. It helps you manage the data structure, so you don't have to go and write your own MPI to manage the grid and parallelize your grid. So DM is for your domain management. It's your data structure and handles communications between different CPUs. And then there are lots of solvers. So time stepping, there are lots of time stepping if you have something which, if you have an equation which requires time marching. If you have an ordinary differential equation or partial differential equation that requires time marching, TS tools is going to kind of help you with that time marching process, and everything is parallel, so you don't have to code everything from scratch again. SNES, those are nonlinear solvers, and within SNES object there are multiple different nonlinear solvers that you can use to solve nonlinear systems of equations. KSP solvers are Kirchhoff subspace solvers, which are a class of projection methods, iterative methods that you can solve linear system of equations. So KSP for linear system of equations. TC object are preconditioners, which again you can use with your linear solvers. And there are different objects, like vectors, to store parallel data structures as vectors. Mat is basically a matrix, and there are different types of matrix. Those are objects that you can store matrices in parallel without writing your own code from scratch. And then index sets, or IS, are for handling general grids. DM is mainly used for structured grids. Index sets, you can use it for unstructured and even point grids. And it also so PETSc itself has been built on MPI, message passing interface, for parallelization, and also BLAS and LAMP, which are basic libraries, math libraries. So it's built on those, and then it provides you lots of utilities, so you don't have to develop your parallel code from scratch. That was kind of a very brief introduction of PETSc from a high-level standpoint. Now, let's write our own first PETSc code. So log into your HPRC accounts. If you're already on the HPRC, then load PETSc. In order to load PETSc, you can do module spider PETSc. It shows you all the available versions of PETSc. And then load this one, 3.12.4. To make sure that everything is loaded, you can do module list, and then it lists all the modules which are loaded. So in order to compile PETSc codes, we need a makefile. And makefile is just a text file that typically has some instructions how to compile a code. And PETSc has its own makefile, and that's just copy and paste of a PETSc makefile. So the next step is to get this to get kind of, the PETSc makefile. All right. And run it. Okay. So whenever you have the PETSc, you can always go to the PETSc website. They have lots of tutorials. They have lots of things, and you can get all those tutorials online. But whenever the PETSc gets installed in the PETSc directory, so dollars PETSc directory is where the PETSc is installed. So if you go to this, you can copy, for example, exercise 50. That's an example 50 of PETSc. So copy this one and also copy the PETSc makefile. All right. So CP stands for copy. Dollars PETSc directory underline directory is where your PETSc is installed or built, or that's the directory which has all these kind of information. The examples, tutorials, release notes. So there's a question, what is this MPI exec? So whenever you want to run a parallel code, that's how you kind of, that's your MPI. MPI execute minus N. It means on how many processes you're going to run. So minus N1, it means that you're running it only on one process. And then you have your code, basically your executable. So when you make a command, and when you do a make command, there should be an executable file created called ext. So you're running that one. And then these ones are PETSc options. These are PETSc options that tells the code, you kind of, you're inputting these into the code. So you can, we're going to talk about it, how we can have options set in, these are runtime options. DA grid X4, it means that the grid, your DA data array in the X direction, has 4 nodes. Data array in the Y direction has 4 nodes, and then you're viewing the matrix. So you're kind of, see the matrix that you're setting up in this example 50. So it says 3 by 3, but I think it's 4 by 4. I think that's a typo. Yeah. All right. So everybody could get the makefile. All right, and compile and run, because later we're going to need it. We want to make sure that we have we can compile our own code. So the first one, the hello world kind of code, that's your first PETSc code. So open a text editor like VI or Emacs, and then hello world.c. Okay. So Emacs, either Emacs, hello world.c or VI.
So we can do it locally on a local text editor. Or...
Yeah. So Emacs and VI are Linux text editors. So just a little bit about what you're doing here. So these are the header files. We're saying that we're going to use the math library and we're going to use the PETSc vec library. Okay, these are the header files. Then main, that's just the typical C code. PETSc initialize is the first command that you should call whenever you want to start the PETSc code. That's initializes your PETSc. Then you can, when you call, the PETSc initialize, you can call other PETSc subroutines. So for example, here we're calling, PETSc printf, and we are using each rank. We are going to print on each rank because we're using com_self. Com_world is going to only be on rank 0. And then we're just printing hello world. Okay. Then whenever we want to end our code, we need to call PETSc finalize. So PETSc initialize at the beginning of your code, PETSc finalize at the end, and then return. Basically, means that your main is done. You're getting out of this. Okay. If you're done with writing this, add this, copy and paste this to the end of your main file. Copy and paste this, copy this. You can open a makefile, like VI makefile, Emacs makefile, the same way. Makefile is just a text file.
Okay, so I opened it and you're saying just put this line at the last.
Yeah.
Add it to the last line.
Or yeah, before the last, I don't know, like, yeah, somewhere.
Or like you can make a new file with it. Okay.
Huh?
You can just make a new file with it.
No.
No?
Because in the PETSc makefile, there are specific instructions, so you can't have a new makefile, right? You need to, because it requires compiling and kind of connecting with the PETSc library and the path and things like that. Those are in that makefile. Let's do the pressure Poisson equation. Now that hopefully you have compiled your first one, and did you run it on multiple cores? Were you able to run it on multiple ones? All right. So yeah, you see the hello world on this. So I'm gonna first, talk a little bit about what we are trying to do. We're gonna solve the pressure Poisson equation. All right. So Laplacian of P is equal to minus divergence of U dot grad U. So we can write this right-hand side as some F, okay? And then we're gonna do it for a Taylor-Green vortex problem. The Green-Taylor vortex problem. So F is known. On the right-hand side, you calculate this based on the Green-Taylor vortex is this, and then this problem has an analytic solution. So it's gonna help us with checking our solution. If we discretize the Poisson equation, we're gonna get to this 5-point formula. And we're gonna solve this equation with both Dirichlet and Neumann condition. And of course, we know Dirichlet condition based on this analytic pressure on the boundaries of the square domain. Okay. This is a 5-point formula, so you have 5 unknowns and 1 equation, so you cannot just get all those 5 unknowns by 1 equation. You need to write it for all the grid nodes, solve them all together. When you do that, you're going to have some a system of equations. A, P equal to F. So it's a system of linear equations. Okay. So P and F, you can call them as vectors, which contains all the information of your grid nodes. So 2-dimensional arrays, all the nodes. Now, PETSc has parallel vectors. So that's the vec kind of, object and matrices, and then solvers which is KSP, to solve this equation. Okay? So to have this parallel data structure, we want to use DM. DM is the parallel data structure in PETSc, which manages communication between all these structures, vectors, matrices, and solvers. So DM is your communication management. And then, of course, DM also manages the information between these structures, vector and matrices, and also your mesh data, your grid data. Okay. Let's solve this equation. That's all we're gonna, you're gonna modify that hello world. You're gonna modify hello world and add this to your hello world to kind of, you know, start building that. It's a very good programming practice to create data structures in order to pass, if, for example, you have, you want to pass to a subroutine 10 different parameters. For example, you want to pass your data structure, you want to pass your grid size, you want to pass your vectors, and all these things. Instead of, you know, passing them one by one, lump them together as one variable. So create a new data structure. We call this user context. So we're defining a structure called user context, and we have all of this within that structure. So copy and paste this on before your main file, your main source in your hello world. So copy and paste this, or basically write your user context on top of your main. Yes.
Why do we include just the SNES header file?
You can. What?
Why use SNES?
Oh, SNES, because SNES also has KSP. But yeah, we can use KSP.
Okay to use just the generic PETSc.h header file.
It might not be enough, because if you just use general PETSc.h, you might not have SNES or KSP or these things.
Okay.
But whenever you have SNES, and SNES also has KSP and all the other things there. Yes.
We don't need a separate header file for PETSc vec, right? So this is
No,
not
no.
example.
Exactly. That contains, you know, vec, matrix, KSP, all these things. So you don't have to have, that's why I kind of don't put SNES on that. Because it covers all of those.
Even the math.h is included.
Yes. Yeah. So yeah, that's why. So underneath this, define your user context. Everybody copy and paste. And then do another make hello world, make sure that there is no issues in compiling it again. Let me give you a general overview of types of parallel data structure that we can have, or types of parallelism that we can have. MPI, in the MPI, which is the standard for message passing interface, you have distributed memory systems. So you have a CPU with some memory, you have a CPU with some memory, you have a CPU with some memory, and all of them are connected together by your network interconnect. So you have part of your information here, you have part of information here, you have part of information here, you have part of information here. But maybe to calculate something here, you need some information from here. That's how kind of, you know, MPI can tell, oh, you know, send information from this rank, from this CPU, from this memory to here, and back and forth. Okay. There is another one, which is shared memory. So you have a big memory and all the CPUs are connected to this. And that's by OpenMP. So you don't have to send memory from, send one information from one memory to the next and so on. So that's kind of, you know, the shared memory system. And so OpenMP, open multiprocessor kind of, you know, a standard. Now, for distributed memory systems where we use MPI, yeah, you can of course use MPI, but then you have to use MPI subroutines and things like that. It can be a little bit challenging. PETSc makes this data parallelization easier. So you rarely have to use MPI subroutines. And one way is kind of, by this DM data structure or domain management. Think about you have some grid. PETSc automatically can break your domain onto different processors. And each of these processors, each part of this mesh is allocated for one memory. Okay? So this is on rank 1, this is on one memory, this is on one memory, this is on one memory. This information is on your local node. But sometimes for our discretization, whenever we want to calculate, for example, this node, we need information from the neighboring node or rank or memory. Okay. So what it does, it creates some type of ghost node. We call this, which are at the boundaries of your memory, we call these ghost nodes. Okay. On a structured grid, you can have the same things. The ghost nodes are also kind of, where we transfer information. So this information comes from this node to here. PETSc has this VM object that creates this kind of, breakdown and breaks your grid nodes into different processors and allocates this part of the grid into this processor, this part of the grid into this processor. So it does it for you. And VMDA is for a structured grids. You have two choices for these ghost nodes, which we call a stencil. Either you can have a star stencil, which means that you also have nodes from here, or the box stencil, and this is the star stencil. So it's only on neighboring ones in the I and J direction. You don't have this I plus 1, J plus 1, I plus 1, J minus 1, and so on. You only have this a star, this is the box stencil. Okay. And this numbering, so processor 0, processor 1, processor 2, and so on, we call this rank. We call this rank. And rank 0 is typically your processor 0 or first rank. Okay. Or rank 0. We talked about rank and size. So let's use some MPI subroutines so you can see it. So after the PETSc initialize, define two variables which are integers, PETSc int, rank and size. So copy and paste this after PETSc initialize in your code. So MPI com size and MPI com rank gives you the size, the number of processors that you have, on how many processors your grid is distributed on, and also the rank that you're working on, which processor you are. And then after your hello world, and also we want to print out the rank and the size. Okay, so copy and paste.
Rank is the number of processors.
No, size is the number of processors. Rank is the processor on which at that moment it's being run on.
The size would be one value.
Huh?
Size would be one value, or
Size is going to be one value. So let's try it. So copy and paste this into your hello world right after the PETSc initialize. Then do again, make hello world and run it and see what you get. And then you can again run it with MPI exec or MPI run it on 1 running on 2 and see how the size varies with minus n value that you're setting. All right. Yeah.
If we ask for more than what the computer can give us, this is just processes, right? So
Yeah.
wouldn't be just serialized? So like, let's say.
Oh, yeah, that's not gonna work. So it's actually you're gonna see that your performance is gonna decrease.
But
because-
still go in a serial mode.
Not really, it's not gonna run on serial mode, it's gonna wait for the processor
finish.
to finish and then, yeah.
Take out the.
It depends on, your computer architecture. Yeah. But yeah, so did you see the relation between size and the n that you put in the MPI exec? And then you see when you run on size 4, your rank is gonna be 0, 1, 2, 3, correct? Did you see that? All right. So PETSc self is basically the communication. It's the communication for each of the processes. So if you put volt, it's only for rank 0. All right. Now.
Oh, so world equals 0?
Yep.
That's how that works?
Yep, volt, you're gonna, for example, if you put volt here, it's only gonna print it once for rank 0. You can test it. Change self to volt, and then you're gonna see it's only gonna print it for rank 0.
The world doesn't give you any info on the run at the time. It's only.
Yeah,
step
it's
from-
only for rank 0. Sometimes you want only, print something, not for all the processors. Only you want it, okay, on rank 0. That's where you kind of, put PETSc volt.
When we are adding the arguments of the communicator being the word communicator for MPI size and rank, is this asking so it's the 0th rank asking all the other processes for.
This one?
Yeah.
Yeah, so yeah, you have to do volt is your MPI volt. It's all of them. So what is the size of that volt? Not just on one,
Yes.
right? Okay, that's why you have to have communication size, you have to have this.
So if I do a self on that one, each process would say that I am only one, and then.
I guess so, yeah. I haven't tried it, but yeah.
I've tried it once, the rank, so it just prints out 0.
Oh, yeah. So yeah, it should be volt to give you size, yeah. We want to now create that DA or data structure. DMDA, your data management data structure, which creates your parallel grid. Your data management, which create your parallel grid, depending on how many processors you're calling. And PETSc does it with DA. So let's create, a subroutine. PETSc error code is just whatever, that subroutine is gonna do, and then do the create context and pass your user that we had defined into here. Okay, so user is the variable for your user context, the data structure that we had created before. That's all the data that we're gonna pass. So copy and paste here. We're gonna create a new subroutine, all right? And then we're gonna create the DA here, the data array here. We're gonna get the grid size. So let's assume that we're gonna have a NX, your grid 40 by 40, okay? User NX is 40, user NY, the number of nodes in the Y direction is 40. I mentioned we can have input to the PETSc during the runtime. And we do it by PETSc options. We can have PETSc options get integer with the symbol minus NX that you run after your, hello world. You can put minus NX, and then whatever value that you get, it goes to your user NX. Yeah.
What is the difference between the null and the first part and the PETSc now? So
It's the same. They're the same. So PETSc options, again, get int, NX and NY. This is to be able to get this from the command line. All right. So copy and paste this.
Is it separate file? Is it new?
No, 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 no. It's not a separate file.
In the C, hello.
In the hello log, yeah, in the same thing. Yeah.
Inside the int?
No, no, no. It's outside the main.
It's outside the,
Outside the main.
it's like, can I enter it? So I have to enter this below the main, so it's a routine, right? Below or above the main?
Above the main. Yeah, do above the main. You can also do it below the main, doesn't matter that much. But yeah, do it above the main. I think it's better. Because when we call it from the mail, the compiler doesn't give you, oh, implicit definition. It's gonna still work, but yeah. Copy and paste. Yeah, it's a separate subroutine. Copy and paste. Yep. So we got the grid node NX and NY. Now, this is the command line, this is the subroutine, DMDA create 2D that creates that data array in PETSc, create that parallel data structure. So you don't have to go and say, you know, how it does, the PETSc does it for you. Okay, so DMDA create 2D, there's DMDA create 1D, DMDA create 3D, or just DMDA create. Here we want to create a 2D grid, so we're using DMDA create 2D. So the inputs, the communication is your PETSc combo. That's your communication. X body and Y body is if it's kind of, you know, what if you have periodic boundary condition, if you have ghosted boundary condition, you have a mirror boundary condition, you can set none, because we don't have a periodic boundary and we're going to use Dirichlet or Neumann condition. Okay, so DM boundary none, and then the type, we're going to specify the type of the stencil, and this top part is just copy and paste from PETSc document. All this information about different PETSc subroutines are on the PETSc website, on the documentation. So type, you can have, we talked about the stencil. We're going to use the star stencil, I guess. Yeah. Okay. Yeah, we're going to use a star stencil. After that, M and M are the number of grid points in the X and Y direction. Small m and n are the number of processors, the number of processes in the X, Y, and direction. Degrees of freedom in the number of degrees of freedom that we have on each grid node. Here we are just solving for pressure, so it's 1. And we are setting these ones on PETSc side. So we don't have to set specific values. We can set PETSc decide. So depending on how many nodes you can run, it's gonna do this for you. Gonna calculate these for you and break the domain into different sections depending on how many, what is the size of the number of processors that you're running on. Degrees of freedom is 1. Stencil, how many, the stencil width is how many ghost nodes we want. Here, because we are using only a 5-point formula, we only have I plus 1, I minus 1, j plus 1, j minus 1. We only need 1 ghost node. If you were using a larger or kind of, you know, a different discretization, which required more nodes, then you have to use that. Okay, so this is 1. And then LM and LN are local sizes of the grid nodes, which again we put PETSc no, so it can be decided. We don't set anything. That's typically you can do. If you want specific size for your local arrays, you can of course set there, but typically we don't want to do that because we want to have flexibility to run it for different grid nodes and so on. Okay. And we want to, you know, set all the options from the command line, so we don't have to go into the code, change it, recompile it, and so on. Okay. All right. And then user 2D is basically our DA. is a DA that we have defined, and we are storing it in our user.
So what is the one degree of freedom that we have defined in this DM?
That's because we have only one variable at each grid node, and that's our pressure. Pressure. So if you had, for example, you had a vector at each grid node, for example, you had the velocity, U1, U2, U3,
Yeah.
you could set 3.
So can I do
Or
4 for pressure and velocity together?
Yeah.
Okay.
Yeah, so for example, if you had a Q, you can have 1 PUV, you can have 4. Or if you had 5, maybe you had density,
Yeah.
then you do 5, right?
So, for the stencil width, you told that, since we are having 5, like since stencil size is 5, so we just have to put 1 because that one node stores all the ghost information.
Yeah, so think about it. So, for example, this is your boundary, okay? And we are using a 5-point discretization, right? So this node, which is within our one of the ranks, okay? So this is I minus 1 is here. There might be at most this I plus 1, which is on the other one. So we only need 1 node, correct? So that's the ghost node that we need from the other domain.
So that information can pass on. Oh, okay.
Yeah, that's the ghost node that I'm talking about for the formation passing between different nodes. Okay, the same with the J. Okay, if this is inside, we can have maximum 1, which is going to be in the other domain.
So this is not related to the higher order estimation of the grid?
No. This is just based on your discretization and your formula. What are the nodes that you might need? So if you had a formula that everything was local, for example, PI was just some function of all the values that you had on node I. There was no need for a ghost node, right?
Yes.
Everything was local. Yes.
With the DM.
Uh-huh.
This is just, so when we are doing a DM creativity, it is for variables of interest. So let's say coordinates or something. We can't store it in this DM object, or do
Yeah, you can.
we can store it in this DM object and not make a separate DM coordinate.
No. Yeah. You don't have to create a separate game. Okay, so copy and paste this. So that's your DMDA create. Okay, copy and paste onto the new subroutine that you're doing, and then DM set from options. You're setting all the options either from the options file or from the command line. And then after the options, you kind of set the options, you have to call DM setup. Okay, so you create, you set from options, and then you do DM setup. So copy and paste these 3 onto your
Inside the subroutine.
Yeah, inside the subroutine. Yep, just here, below here. You had it up to here, copy and paste below here. Okay. So copy and paste this below that one. Now, we have created our DM object, data array object. Okay. Now we want to create, we want to create our vectors, our pressure, kind of, our variable that we want to solve, and also the reconcile. Okay. All right. So we can do this by, and then, we have 2 types of vectors. We have global vectors and we have local vectors. Okay. So global vectors contain only the local information. Okay. Global vectors contain only the local information. They do not have the ghost node information. Local vectors have this local information plus this ghost node. Okay. So you can create DM create local vectors, DM global vectors. So, and whenever you want to update these ghost nodes, you can easily do this by calling DNDA global to local. So you update all the ghost nodes based on the global values that they have at each rank. So you don't have to do, okay, MPI, communicate or things like that to update this ghost node. If you didn't use PETSc, then you had to do this on your own. Kind of, oh, MPI communicate from this node to update this. With this, PETSc takes care of all those communication for you, makes things easy. Okay. So let's create our vectors that you're interested in. Okay. So let's create a global vector for pressure, and we store it in user P. Okay, that we have defined in our user structure. And then if you have other things, you can use, and I think this should be capital P. Sorry, there's a mistake. There's a typo here. This should be capital. Okay. And then whenever you calculate a vector, then you can do duplicate. Duplicate just allocates memory. It doesn't copy the values. So this creation is just allocating memory for that vector in your on all the ranks. Okay, and then duplicate is going to do the same thing. So you're duplicating user F. Basically, you're creating a new global vector for F for your right hand side.
Is this F associated with the DM?
Yeah, because this is also created based on the DM. It's a duplicate of that.
So when this F is being localized, it will be according to the DM.
Yep. So it has the same data structure as your DM. So whenever you do this, you create the same data structure based on your DM.
And should it be address of F? Or should it be address of F and user?
No.
So because it's below it is.
Yeah. It's already there. And then let's do this also P analytical. Okay. And then let's also do a local vector based on our data array that we have. Okay. So again, copy and paste this in your subroutine below the DM. Yes.
The main.
No. In the subroutine after you have. No. In the same subroutine. So right after this, your DM setup, copy and paste this right after your DM setup.
So this is within the PETSc error code create city.
Yes, it's within that. Exactly.
I did declared the created the subroutine like PETSc error code. So you can call it within itself.
No, I haven't called it yet.
Oh, you just declare it.
It's that subroutine. I'm gonna call that subroutine create from the main later. We're gonna get there. Now we're just writing the subroutine.
Okay.
In that subroutine, we are creating our DM, and then after we create the DM, we're gonna create the vectors.
Okay.
So right now we're just creating all the vectors and things like that. Okay. Yeah.
So this is for a rectangular grid or it works for any kind of shape grid?
This is for your structured grid. Yeah, this is for your structured grid. Yeah.
Why is it that we use?
Huh?
Why is it that we use user F and not the address on this one, and the second one is address of the that duplicate.
Oh, maybe it should be.
And yeah.
Maybe there should be an and here. Sorry, there should be an and here. If there's an error during the creation of those vectors, it sends you, what that error is.
Debug.
Yeah, exactly. So let's talk about numbering. So typically, whenever you have a natural numbering, it goes from 0, 1, 2, 3, 5, 6, 7, 8, and so on, right? That's the typical natural numbering that you can have. But in PETSc, that's not necessarily that. It's like 0, 1, 2, 3, 4, 5, 5, 6, so on. So It's not natural number. Okay, so typically what and also if you have a ghost node, again, the local numbering and global numbering also is going to be different. Okay. So PETSc, whenever you're using PETSc has some tools. Whenever you do global and local, it understands it. And then when you do local to global, it sends the information to the right place. And also, we're going to talk about a few things which is going to help us with these numberings. Now, let's go and create the grid, the coordinate system for the grid. So let's define like another structure called component 2D or 2D component, com2D. Copy and paste this below your user context. User context above your subroutine. Create context subroutine. Okay. And then here we are interested in creating the grid coordinates for our DM. To do this, PETSc has some tools. DM get coordinate DM. You get the coordinate data management because your DM might have only 1 degree of freedom. But if you have coordinates, how many degree of freedom your coordinates might have?
In this case,
Here we have 2. We have x and y, correct? So that's why we're gonna get the coordinate DM, and let's call that coordinate DM CDA, coordinate DA. Okay, we're gonna get this, and then we're gonna say that, okay, we have created our CDA. We're gonna then create G coordinate. Then let's have an array, a 2D array. Let's based on this component 2D. And then let's get our get coordinates in a vector. Okay. So let's do get DM coordinates in some vector called G coordinates. Okay, which we have defined right here. Global coordinates, G core. Okay, so we're gonna get the vector which contains this. All right, we wanna get the these coordinate x and y for all the grid nodes so we can set it. And PETSc, based on its numbering, I said we can't really do this, so we're gonna use this DMDA vec get array. So what does the vec get array does? We have our coordinate DA, and then we have our global vector, and then it puts this global vector onto our coordinates. Okay, onto coordinate array that we can get, and then we can manipulate later. We cannot manipulate the vector directly. Okay, we cannot manipulate the vector directly. We need to get the array for each of these ranks to manipulate, and we do this by DMDA vec get array. Okay. So copy and paste this onto your code. Okay. Now, we want to know this information. So when we were creating the DM for the PETSc, we put PETSc decide to how to break our grid into different on different ranks. With our info, we can get that information. We can get that info. So PETSc has this local info. That's the data structure. And then by DMDA get local info, the first one is over DA. We can get all that information into that structure info. Okay. Then info in that structure, the XS is the starting point on that rank, and XE, XM is the size in the X direction on that rank. So, for example, you had 0 to 40, and it kind of, and you run it on 4 cores. 0 to 20 is on this rank. 20 to 40, so this one is 20 size, the starting is this, so 20 is going to be the XS for rank 1, okay, and also rank 3. XS for these two is going to be 0, this is going to be XM is going to be 20, okay. So you can get the XE, which is the last node, is your XS plus that XM, the size on that one. The same thing, we have YS. So for example, again, 0 to 20, that's your YM, YM, and that's your YE, which is XS plus YM is your YE, the last number. And then that's going to be YS on this node, and then YE is going to be 40. Okay. So we get all this information. Okay. How the grid is distributed when we are running the code in that DM. So we get that information. Now that we have that information, we can have a for loop. So I XS and I less than XE for that local node. Okay. And YS, YE for this. Okay. So the core, we're going to set the value for in that 2D array that we had got using DMDA get array. We're going to get the X values. So we know that the X value is, for example, I multiplied by delta X. And what is delta X? That's the size of your domain. For example, we are solving on a 1 by 1. Okay. And then we have NX. So the delta X is going to be LX, LX divided by NX minus 1. And DY is our grid size. Okay. In the Y. Based on the number of nodes.
Maybe when the DMDA create set uniform grid the coordinates command to.
Yeah, you can use, but I wanted to.
No, do we
Yeah,
have to
you
run
can.
this? So
Yeah, there is an option, set uniform. PETSc has some option, set uniform coordinates or something. So you don't have to do this if you want. If you want to use the uniform grid. But here is more general because then you can have either also a stretch grid and so on.
So when I'm using DM get coordinates on the DA to D object, I've not set the coordinates. So is it just storing, like allocating memory to the vector and
Yeah.
And then when I use DM get coordinates onto G code, so G code just has garbage values that have to vector.
Exactly. That you need to set. So you're setting these values. And note that if you do not use YS and YE, you're going to get a segmentation fault. Okay, you're going to get a segmentation fault because if you, for example, you're on this one and you're setting XS as 40, you're going to get, oh, this one doesn't exist on this one. That's why you have to use this info, and it makes things very easy. Okay.
So what data is in info? Like,
Yeah, the starting point.
Okay.
And the size on each of those your ranks.
oh, so M is just like integer of total length.
Yeah,
So X, M, Y, M.
XM, exactly.
And is that like all that's in? info, just
exactly.
these?
Just, yeah, the information about your grid layout, your data structure layout, how they are distributed among processors. Okay. All right. And then, of course, we can also define beta, which is dx over dy. So also copy and paste this in your subroutine, create context subroutine. Okay. And then, yeah.
So the. I mean, PETSc's eventually gonna take care of stuff, for actually assigning like values for sensors and whatnot.
Yep.
But, we go back for a second.
Sure.
So like, you know, length of the vector that I was just given. Great, that's my M value.
Yeah.
But for the,
Oh, this one is no, it's on each processor. It's not your NX or NY.
yeah. So
Okay.
like if for our example over there,
Uh-huh.
40 is the total.
Yeah.
that we gave it.
Yeah.
But it gets broken into 4, so each one's 10.
Exactly.
10 would be M. Right?
Yeah, yeah.
What is S?
XM, huh?
Yeah, XM.
Yeah.
What would S be? Would it be 111? Because does it like?
What is, oh, YS?
Yeah. Like,
That's the starting location. So
so
here on rank
actually-
0, that's your start. That's your 0. And then you have, that's 10. Here I, put the example of 20. So your XE on this one is going to be 20. But then the XS for this one is going to be 20. And then the size is going to be 20 here. Okay? Is it clear?
Yeah.
Why did we set NX and NY to input or MX and input or MY as we have defined it in the user context itself?
If I, what
Like
did I have
NX
what?
and NY are set to the DMDA
Yeah.
info value.
So,
But we have already defined NX and NY, right?
it's the same thing. It doesn't matter. Yeah. But I wanted to kind of mention MX is the total global size. XM is just your local size. So this is MX, so don't confuse the two. MX is your total kind of, 4D. This is XM is your local length, local size.
That is.
Yeah, well, yeah, that's why I kind of put it there. That's why I put it there. So yeah, to make sure that you notice it, okay? Yeah, you had a question.
This excess is the total number of nodes, including the ghost node, right?
XS,
Yes,
that's your starting index.
starting.
A starting index. So this one, no, this is without the ghost node.
Without the ghost.
Without the ghost node. So XS is without the ghost node. There is GX, that's the ghost node number.
Yeah.
So there's a GX that includes the ghost node. Okay, if you want to use that, use GX.
Okay, but whenever we are actually computing, so we have to start from excess.
Yeah.
So the ghost node is only taken care when you are actually allocating between the ranks.
Exactly. So always, and then because this is a global vector, we are going from XS to XE. If it was a local vector, and then, so if you had J plus 1 here or J minus 1, it might give you a segmentation form. If it's a global vector, you have to use local vector.
Local.
Yeah. All right. Okay. So we're gonna do the same thing. We're gonna get the array for our P analytical and also our right-hand side, which we know from the Green-Taylor vortex analytical solution that we have. So here we are kind of, again, we're getting the P analytical in a P array, and then which is a 2D array, and then the F, again, another F array. Okay. And then we are setting PJI. Okay. And these are just because these are 1D, there's no component. These are just PETSc real kind of, real type. And then we're just, setting this equal to this. Again, because this is J and I, we can easily, and these are global, right? These are global. So we can easily set the global values. And we are not going to I+1 or J+1 that need local vectors. So easily we set these values, okay? Now, after we are kind of, done with setting, we need to do a restore array. If you don't, you're gonna get a memory leak. Okay, so again, copy and paste, and that basically concludes your subroutine. So do a restore array for your P analytical, for F, and also for your coordinates. Okay.
What is this doing?
Huh?
Is this like, I just did quadrant 1, so now I need to do quadrant 2, so I need to clean out? Or is this, I did iteration 1, I'm about to do iteration 2?
No. It's when you get the array, you allocate memory, you put the array, and you put kind of, you take the information onto your local array. When you restore it, you put that information, restore it into your vector. That's it.
Oh, restore puts it into the global, like.
Exactly, your P analytical vector. Restores the value and destroys your array. So-
But like.
So allocate the element.
So you're saying, take the data that I now have in P analytical and shove it back up into P.
Exactly. That PETSc object vector. And then kind of, that vector, that array P, it's gonna be get removed from the memory. If you don't, you're gonna have a memory leak. Okay. All right. So now that we are here, copy and paste this, compile your code and see if it gets compiled up to this point. Yes. Yes.
Does it have to be always, we have an even number division of the total number of?
No.
It can be anything.
PETSc allocates based on the number that you have and the size, how many processors that you want. PETSc kind of, breaks it down.
Okay.
And yeah, it doesn't have to be even or anything. PETSc for you, it might have, it tries to break it into even parts. For load balancing, sometimes what it might be, 1 plus 1 minus, it tries to keep it close.
And vec restore array handles the free
Exactly.
things.
Yeah, we don't have to free or deallocate that memory. Okay. All right. So did you have, like, in the main, did you call the create CTX subroutine? Oh, we didn't?
No.
I thought I had it somewhere. No?
Yeah.
Oh, yeah, no. On the first line. So put this in your create CTX / user, put it in your main. Okay? Because we want to call this from the main after the initialization and those rank things. Okay? So in create CTX, we created the DM, we created our vectors, we set our coordinates, and we also set the right hand side and the analytical solution. We are doing this in all create context subroutine. Create CTX.
Even this one, right?
Yes, these are all, yeah. And then at the end, so this is the last part. Return 0. That's the last part that kind of close down your create CTX subroutine.
This is just the next generation method and the boundary element.
Yep. So we created the DMBA. the grid, yep, the data management for the PETSc, created the vectors, created the mesh, created the analytical solution, and the right-hand. And we can do it once because the right-hand side doesn't change, the analytical solution doesn't change, the grid doesn't change, so we just do it once. So create contacts and then pass user, do it on the main. Let's go and talk about creating the solver. Okay, so KSP is the linear solver. Okay, so first we create the solver, it allocates memory and options, and then we are setting the DM for our linear solver as the DA that we had created. Okay, so it kind of sets the data structure. So we created the vectors and everything based on the DA. So they are all compatible. You cannot create your, for example, KSP with a DA and then have the vectors created with a different DA. We want the data structure underneath all of these to be consistent. And then set application context, basically our user. So when passing our 2D, our DA to the KSP, we're going to have access to our user context as well. And then KSP set compute operators. There are different ways of doing this. Set compute operators is basically setting your matrix A, your operator, which is your left-hand side. And we're going to do this by KSP compute left-hand side. It's the name of subroutine that we're going to write to calculate that matrix A. And then the user is basically our context. And then we're going to set the options for the KSP from the command line, KSP set options, and then KSP solve is after it's set the options, it can solve it. Okay, so copy and paste this in your main. Copy and paste this in the main after where you call the create CTX subroutine. Now, this is kind of just a repeat. KSP set compute operators, sets the left-hand side of our operator matrix A. We need to start writing the compute left-hand side subroutine. Okay. We can also use the KSP set compute right-hand side and have a function to calculate our right-hand side, but we already because it was known and it was a single value, we don't have to do that. We have already done the set the right-hand side F from in the right in our create CTX. Okay, so let's start the subroutine. Okay, copy and paste this. These are again, we're gonna get the info to know where we are. Okay, we're gonna get the information of the grid layout and the distribution, its parallel layout on different nodes. We're going to define some variables. I, J, K are your integers, your nodal values and things like that. And then math stencil, because we're going to set matrix. Math stencil is, we're going to define this. It's going to help us go from natural numbering to the PETSc numbering. Row is the row of that matrix. Column or the columns within that row, and we are going to use 5 of those. And then PETSc scalar, that's just a scalar value, again size 5. And then math Lula space, we're going to need it if you're using Neumann conditions. We're going to talk about that as well. So copy and paste this in your as a new subroutine, and then we're going to set the coefficients for matrix A in here. Okay? So for each I and j, we had our equation, correct? For each I and j, we need to set the values of the matrix. So rho dot I, remember it's we're gonna set it as I is the grid node. Rho dot I gives us the PETSc numbering associated with the natural numbering I. Rho dot J gives us the row value, again, associated with this INJ number, PETSc number.
Oh, okay.
So you for row, we're gonna use it later. Okay, we're gonna say I and j are our grid node, and then row dot I and row dot j are gonna be used to find the location based on the PETSc numbering of our matrix. Okay, and then we are setting if we are on the boundary. I equal to 0, j equal to 0. So on the boundaries of our domain, we're gonna use this equation. We're gonna use this equation. P is equal to some P. Okay. And that's gonna be your P analytical, which is no, with the Dirichlet boundary condition. So the coefficient here is just gonna be 1 on the diagonal, correct? That's a diagonal. For other cases, that's our discretization, correct? So we are setting the value V0, it's for column I and j minus 1. So it's for I, j minus 1. What is I, j minus 1? The value, the coefficient, is beta squared. Okay? That's our discretization. We are setting the coefficient as beta squared. Okay? And then the column for this value is I, and the j for that one is j minus 1. Again, column is going to give us where it is in that matrix, okay, based on the value that we have, I and j minus 1. Okay, we do the same thing for I minus 1 and j. I minus 1 and j, what's the coefficient? 1. So we're setting at 1. And then I and j, that's our diagonal. We set it as 2, 1 plus beta squared. That's I plus 1 and j, which is 1, and then beta squared for I and j plus 1.
So in Max stencil objects are just a communicator between the grid and the matrix itself.
Natural numbering
And the matrix.
and the matrix numbering. Yep. And that makes things very easy. I don't think you could do it because the PETSc numbering, as I mentioned, it's very, very different than the natural numbering that we have. So it has all these tools to make things easy for us. Okay, and then here we set math set values as stencil. So that's our matrix, our operator A. Okay, and we are setting 1 row. And this is the row number that we are setting. We are setting 5 values. These are the columns that we're going to have. And those are the V values. These are the coefficient. And we're saying insert the value.
So is it like looping through the rows so that one is 1 row at a time, or?
Yeah, it does it for all the.
That is for all the grid
For
points,
all,
right?
yeah, you do it, and then you set it. You set the values row by row, and it's on a local process.
Okay.
Right? Okay. So you set all the values into the matrix. After you're done within that loop, you kind of you say math assembly begin, math assembly end. It assembles the matrix in parallel. Okay, and then these are I have kind of math Nula space. We can talk them about later, and then return and go back. And this is all set. and this is also, okay? So copy and paste this, and then compile again, and I think we are ready. We are ready kind of, to visualize. So we can now go back to your main, and copy and paste this. This is PETSc viewer. That's basically input and output. That's parallel input and output. So we're calling the object name, and then we're going to create a PETSc viewer. And then we're going to set the viewer type as PETSc viewer VTK. And then we're going to set the mode as a file mode write. And then we're going to set the file name as pressure.vts. So vecview, PETSc viewer destroy after kind of, vecview is basically sets the output. And then PETSc viewer destroys our viewer. And at the end, we can also, do a calculation of the error with some, again, PETSc subroutines, which calculates vec_axpy subtracts two vectors from each other. Okay? And so ax minus py, so that's p minus p analytical, and stores it into the user p. Okay? And then we can take the norm of this, and that's our error norm. And then you can also print that. So also at the end, we always want to, free all the memory that we have. And then, so that's why we have KSP destroy, DM destroy, and then PETSc finalize, and then destroy CTX. You can also destroy or free all the memory that you have, all the vectors. So again, copy and paste this. And after that, let's run it.